All right, so today we're going to talk about the Swift type checker, and we're going to talk about some recent improvements in the Swift 6.3 development branch, as well as kind of more ongoing work on the main branch. And I'm going to intertwine all of my explanations because I don't have a lot of time. All right, so let's get started. So here we have this complicated expression, and I'm going to start with Swift 6.2, which for us compiler developers is ancient history at this point, but of course it's the latest public release. And when I compile this program in Swift 6.2,
sorry, we lost this microphone. Oops.
okay.
And it's important for the video.
Okay, so when I compile this program in Swift 6.2, the total time to run Swift C on the command line and do everything, linking, optimization, it's around 150 milliseconds. Of that, about a millisecond is type check time, so it's not bad. And then let's say I want to make my code a little clearer to understand, and I add a type annotation. So I'm going to declare that the type of my thing is int. And now, it's still very fast to type check, a millisecond approximately. But maybe I want to do the same calculation with unsigned integers instead. So now, bad news. The Swift 6.2 compiler does not like my expression. And you'll see there is a happy ending to this, but we're just going to go with it for now. So why is type checking Swift not like completely trivial that it can always just be solved in under a millisecond? And basically, when you have expressive language features together with static type safety, it's kind of unavoidable that there's some work to be done at compile time. And in particular with Swift, there's several language features that allow you to write very expressive code. For example, I can use operators like plus to add integers and doubles. I don't have to invent like a new operator just for floating point math. More generally, I can overload functions, so I can give the same name to related operations. And just a quick aside, like this does not apply to like overloading argument labels or arity. That is kind of trivial. Another interesting language feature is literals in Swift. 0 could be an integer or a different size integer. It could be a float. Like we don't have weird syntax like for different types of literals. Another one is closures. You can infer parameter types. So inference flows in both directions in an expression. Like I don't have to declare the type of x in my closure there. Implicit conversions. And these two I'm not going to talk about. But you can imagine that also like here I've got a rectangle and I'm passing it as a shape existential without having to wrap it in a shape existential by hand. That kind of thing also creates additional work for the compiler. And so how does the compiler deal with like all of this stuff that you can do? Well, we type check one expression at a time generally, except for multi-statement closures, but we're not going to worry about that. And there's kind of two key concepts that are important in the implementation is type variables and constraints. We basically create a new type variable for every part of the expression that has an unknown type that we need to figure out. And a type variable can stand for any concrete type. But then we look at the syntactic structure of the expression and we generate constraints to relate these type variables. And the constraints restrict the concrete types that the type variable can have. And the goal is to search for some way of assigning a fixed concrete type to each type variable in a way that satisfies all of our constraints. Okay, and a classic result in computer science is like this kind of thing. NP hard, like we don't have to look at the definition of that. It basically just means that the search might take a long time because there's a lot of possibilities to consider. And we might have to stop and give up. So let's make it concrete and look at like the plus operator in Swift. We've got overloads for integers, unsigned integers, different size integers. You've got floating point types, strings, all this other stuff. There's some generic overloads. And if I just have a single expression that consists of plus and nothing else, then we have to create a type variable to stand for the type of that overload. and we generate a disjunction, which is just a fancy way of saying or, that lists all those possibilities for the type that this overload might have. And literals, like 0 can be a float or an int or even my custom type that implements the integer protocol. And, all of those are just written as 0. And there's this kind of misconception I've seen a few times where a literal also becomes a disjunction of like every single type that conforms. That's not how it works, because that would be completely intractable. It's a lot simpler than that. We create a type variable for the literals type, and then we say that it has to conform to this protocol. We type check the remaining expression, and if nothing else forces out literal to have a specific type, we give it the default type, which for 0 is going to be int. And what does reasonable time mean when the compiler complains about reasonable time? Well, it's not wall clock time, because that would be weird and non-deterministic. Instead, the compiler basically counts operations, and the important one for us is going to be scopes, which are basically jargon for a combination of choices. There's also a memory limit, but we don't have to worry about it. So let's look at our expression and kind of vary the number of plus signs. And you can see in Swift 6.2, when the number of plus signs increases with the one that's annotated with int, the number of scopes scales linearly. But if I put uint in there, it kind of increases very rapidly. It turns out to be exponential with a little bit less than the number of overloads as the base. And here's the good news. If you download a developer snapshot for 6.3 from swift.org, then this expression is fast with a uint as well. And if you look at the scopes in Swift 6.3, you once again have linear scalability now. So, thank you. And actually, this particular optimization, I didn't work on it. It was a colleague of mine, so full credit to Pavel. But it raises 3 questions. So, the inversion was fast in 6.2 because 6.2, it did this kind of pre-processing of your constraint system before it started solving to try to guess certain things up front. And the uint version is slow in 6.2 because this pre-processing was insufficiently general. And 6.3 gets rid of that, and there's a new disjunction selection algorithm. So what does that mean? Well, I'm going to simplify my example so that there's just one plus sign. And I'm going to pretend there are only 2 overloads of plus. And here's my syntax tree, and I'm going to do disjunction selection, but I'm going to use a very bad order. And you'll see it will take a lot of steps. So let's start with, here, we have this one bit of type information here is that the result of the plus is a uint. We don't know anything else. So I'm going to pick the first overload for the first multiplication, and that one's the int overload, and so far everything is fine. And then I'm going to make another bad choice. I'm going to pick the first overload for the second multiplication, and again, we don't have any problems yet. But now when I pick the first overload for the addition, then I see that the result type doesn't match the type that I expect. So I have to throw away that choice and backtrack. And now I try the other choice for the plus, and now the parameter types don't match. So I have to backtrack again. I've run out of choices for plus, so I have to try the next choice for the second multiplication. So far everything's fine, and then I try the addition. Now I'm stuck here. I tried the other one. Now I'm stuck here. Now I have to backtrack twice. I'm back to the first multiplication, and now I try the second overload of that. And then I kind of keep going. Okay, bad news, backtrack. Okay, stuck here again, backtrack again. Oh, this looks promising. No, not quite. Here we go. All right, 14 steps, and we found the solution. Okay, and now let's try disjunction selection with the good order. Now, since the only piece of type information I have here is the result of the plus, it seems logical that I would start looking at that first. So we try the first overload. That doesn't work. Try the second overload. All so far so good. Now I can try either of the 2 multiplications. Let's pick the left one first. Again, we have a mismatch with the first choice, but the second choice succeeds. And now I've just got the second multiplication, and the first choice doesn't match, but the second choice succeeds. In 5 steps, I found a solution. Now notice how in both cases, I've attempted every disjunction and every choice, but just by doing it in a different order, I've cut down the amount of work that I have to do. So that explains why, some of these expressions are now faster at type check in 6.3. Now, it might seem that it's completely trivial to always pick the right disjunction to solve next, but it's not. So here's a more elaborate example with, an array literal. It's got some arithmetic expressions in it, and then we map over it with a closure. In Swift 6.3, it gives up. It throws in the towel. Now, with some changes we're working on, this whole expression type checks in 3 milliseconds and only 78 scopes. That's very little work. Thank you. So basically, that's like the Swift constraint solver game, is you have to try every possibility, but you can pick which possibility you try next. And then another more advanced optimization, I'm not going to demonstrate it in action. It's a little harder to explain, but you can also skip certain choices if you're absolutely certain that they cannot participate in a valid solution. And here's an example where this more advanced optimization helps. So, you've got some array subscripting, bitwise arithmetic, it's just doing a bunch of stuff. And Swift 6.3, it does successfully type check this expression, but it takes 3 seconds. That's pretty slow. The whole return statement is a single expression here, but that's still a lot of time. And we're almost halfway to the complexity limit, so if you add a couple more things there, it might be too complex. With some changes we're working on, this now takes 36 milliseconds. And there's still room for improvement here because we enumerated 970 possibilities, but 100 times faster is not bad. And finally, for my last example, we are going to look at, when all else fails, and, given that for theoretical reasons, you will sometimes see this too complex error showing up. So here's an example where we have an invalid expression. And the reason it's invalid is because there's no overload of plus for ints and strings. And, it's unfortunate, this is not the end state that we want to be in, but it does end up being too complex. And in Swift 6.2, we get a too complex error and it points at the first line of the closure. And then actually someone on the forum said, well, if I have a multi-statement closure like this, can we at least point the error at the statement inside the closure that was too slow? And indeed, that was a very easy change. So in Swift 6.3 developer snapshots, again, you'll see this improvement here where in a multi-statement closure or like a result builder, like a Swift UI view, if it does have to give up, it will at least tell you how far it got roughly. Okay, and some more details. So all of these examples are in the test suite, and they were originally reduced from bug reports, and we have both slow expressions in the test suite, so we can kind of chip away at them and make them fast over time. And then we also have, fast expressions there just to make sure they don't regress. And finally, a few months ago, I had this forum post with kind of more details about some of this stuff. And some of the stuff I talked about, or like both of the features I talked about in 6.3 are now part of the developer snapshots, so they're kind of done. There's a disjunction selection. There's another optimization that I didn't discuss in this talk. And then some of the further stuff that is detailed in the forum post is what we're working on now. And I was showing you the examples of those new expressions that are fast. That's all I have for today. Thank you very much.